Hello everyone, my name is Nguyen. I'm a graduate student of the School of Chemical Engineering at Oregon State University. And today would like to present a poster summarize my current research titled AP-XPS study of thermal decomposition of acetic acid on palladium-111. The objective of the study is to learn more about the surface chemistry of acetic acid on metal surfaces, since it is a good model for other oxygenated molecules. The previous DFT study on this surface reaction has shown that acetic acid decomposes on palladium-111 in two different pathways, the DCM pathway to produce carbon monoxide and DCX pathway to produce carbon dioxide. The study also suggests that in the presence of co-absorbed water, the reaction will shift toward the DCX pathway to produce more carbon dioxide. So in order to confirm this hypothesis, we perform an experimental study on a single crystal palladium-111 using an integrated various temperature AP-XPS in tandem with AP-stm spec system. We were able to obtain 4 data set from 4 different exposure of acetic acid on palladium surface with and without co-absorbed water to observe whether or not the presence of co-absorbed water changed the reaction pathway. Each spectra composes of 5 components. The surface components are carbon-carbon, carbon monoxide adsorbed, the carboxyl carbon chemisorb, and the 2 other components are the methyl carbon and carboxyl carbon from the acetic acid gas molecule. When comparing the exposure of just pure acetic acid to the exposure of acetic acid in mixture of water at a similar total pressure, 1 millibar, you can visually see the growth of the carbon monoxide peak on the shoulder of the carbon-carbon peak. To put that observation in terms of number, reported here on table 1 is the relative components area and the ratio between the surface components. And from the first comparison, as you can see, the ratio of carbon monoxide to the other 2 surface components increased by 2-fold when acetic acid is exposed in mixture with water at 1 millibar. Now moving on to the next comparison is when we expose acetic acid with water at elevated temperature, 385 Kelvin. As you can see in the spectra here, the carbon monoxide peak continued to grow. And as reported in table 1, the ratio of carbon monoxide to the other 2 surface components continued to grow as well. And for the last comparison is where we expose acetic acid in mixture with water at approximately 2.11 millibar, a higher pressure to see how the reaction pathway will behave varying by pressure. And as you can see, the carbon monoxide continued the trend as is more visible on the shoulder of the carbon-carbon, and the ratio of carbon monoxide also increased. To summarize this, XPS spectra shows an increase in carbon monoxide accumulation on the surface in the presence of co-absorbed water. Now I've only talked about carbon monoxide, and then how about carbon dioxide, right? Because that's the product of the other pathway. This is when the mass spec with a gas analyzer comes in. This instrument allows us to identify and monitor the 28 and 44 AMU mass peak, characterizing the carbon monoxide and carbon dioxide gas species respectively. And we see how, and comparing the exposure, which is acetic acid, to the exposure of acetic acid with water at 2 different pressure, you can see the ratio of carbon monoxide dioxide to carbon monoxide increases from 2.11 to 2.82 and 2.65. Now, the mass spec data shows an increase in carbon dioxide to carbon monoxide ratio in gas phase in the presence of water. To tie everything together, I would like to pull out some preliminary conclusions. The data suggests that the reactivity increases with temperature and pressure. Both of the pathway are enhanced in the presence of co-absorbed water, and we see more carbon monoxide accumulated on the surface and more carbon dioxide is being produced in gas phase. For future work, we would like to obtain a control of the mass spec of just gas phase without palladium sample to see whether or not the change in the ratio of carbon dioxide to carbon monoxide is due to the surface reaction. And we would like to also perform a high temperature XPS experiment to get more information about the decomposition. I would like to acknowledge the AP-SCL for allowing me to obtain this data. It is a user facility part of the NSF and NCI network, and more information can be found in this link right here. And I would like to also acknowledge the funding organizations, NSF and NNCI. Thank you for your attention, and I'm looking forward for your questions.